folks, welcome to 5.2, the definite integral. So before we talk about the definite integral, I want to start with a comparison between indefinite integrals and definite integrals. So when we think about indefinite integrals, we think about the general case, okay? These are the cases where we have that plus capital C at the end, all right? So this is a general case in the indefinite integral, and our notation usually looks something like this. We have our integral symbol of some function, dx, and when we solve it or evaluate it, we'll get capital F of x plus c, okay? Now, in comparison, let's take a look at the definite integrals. So the definite integrals would be considered the specific case for an antiderivative, and the notation looks something like this. The integral of f of x dx. And so that part looks the same, but for definite integrals, there's a lower bound, or a number on the bottom, and an upper bound, or a number at the top. And at the end, you should get a number as your answer. If you don't get a number, then you did something wrong, okay? So we should get a number as our answer. And that number represents the area between the curve and the x-axis starting at A and going, or rather stopping, at B, okay? So it's the area between the curve and the x-axis, starting at A and stopping at B. Now, before we move on, let's go back to our indefinite integral and maybe talk a little bit about this answer. So our capital F of x represents potential area. However, this plus C could be considered a vertical shift in the graph. Okay? So because there's a vertical shift, we don't get an actual number that tells us the area because we don't know how much taller, how high above the x-axis it is, or how far below the x-axis it is. And one last note for our definite integrals, this one should have no plus c, okay? So you've got your general case with the plus c, specific case with no plus c, and then the integral, which gives you a f of x plus c, and then a definite integral, which gives you a number, and that number represents the area between the curve and the x-axis, starting at A and stopping at B. Okay, so let's take a look at this problem here. We're going to evaluate definite integrals with geometry and with what we know about antiderivatives. And so we're going to start with this example right here. The integral from 2 to 4 of 2x plus 3 dx. And so what I'm going to do is I'm going to go ahead and graph the function 2x plus 3, and I'm going to set up a little xy table to help me graph. I'm going to start with an x value of 2 because that's the lower bound. And then I'm just going to count by 1, so 3, and then 4. And I'm going to plug 2 into this function and see what I get. So 2 times 2 is 4, plus 3 is 7. 2 times 3 is 6, plus 3 is 9. 2 times 4 is 8, plus 3 is 11. And so that gives me enough information to plot a graph of the function. Now, I'm going to sort of generalize here. So let's say that this is the point 2, 7. So we'll say that's 7, and this is 2. And then we've got a point here and a point here. So this is 3, this is 4, this is 9, this is 11. And if we connect all of those, yours is probably more accurate, but you should get a straight line. It is a linear function. And I want to go ahead and mark off where I am starting and stopping. So we're going to start at 2, x equals 2. So this is my starting point. And I'm going to go ahead and stop at 4. So 4 is my stopping point. Just fix that a little. Okay. So if I look at this, what shape do I have in here? Well, I have a trapezoid, and it is a trapezoid that is sort of standing up, okay? So these trapezoids kind of go like this, and that means this side is the height. We could consider this as base 1 and this is base 2. So when we find the area of this region, okay, so we'll call this the region we're looking for, that area we can use the area of a trapezoid formula. So 1/2 base 1 plus base 2 times height. And let's plug in our numbers. 1/2, let's see, base 1 is the green one, and I went up 7 units, plus base 2 is the blue one, and I went up 11 units, and the height is this distance right here, which is 2. Now, I can simplify this a little. By canceling the 2 and that 1/2. And then I know that my final area will be 7 plus 11, or 18. Okay, so that's what it looks like if we're able to solve it with geometry. Now, we can't always solve it with geometry, but it's a good option to have if it's a circle or a triangle or a trapezoid or even a rectangle, okay? So it's good to know those formulas could be a shortcut for you. But on the flip side, let's see how we would have solved this using antiderivatives. And so I'm going to go ahead and rewrite the problem here. So I've got the integral from 2 to 4 of 2x plus 3 dx. And so if you think back to 4.10, we were talking about antiderivatives. We need to find what function gave us a derivative of 2x plus 3. So I'm going to start with the 2x. So the 2 is a constant, so I can keep it out in the front. My x is currently to the power of 1, so I know that it came from a function that had a power of 2. And then the coefficient is going to be the reciprocal of that, or 1/2. Plus 3 is just the constant. And where did that come from? Well, it just came from 3x. And at the end, I'm going to go ahead and put that bar. I'm going to put the 4 at the top of the bar and the 2 at the bottom of the bar. Now, you could plug in the numbers now, but I find that if I reduce things first, that it's easier to plug in numbers. So, for example, this 2 and this 1/2 reduce to 1. So I can write this as x squared plus 3x, and I'm going to put in a 4, and I'm going to put in a 2. And so this gives me 4 squared plus 3 times 4 minus 2 squared plus 3 times 2. And again, the green number is our bottom bound, and that's the one that gets subtracted, whereas the blue number, just had to check that I was right, the blue number is the upper bound, and that's what we plug in first. Okay, So let's simplify this. We'll get 16 plus 12 minus 4 plus 6. And when we clean that all up, we should get 18 for our area. Ooh, sorry, I don't know why it's freezing so much on me. Okay, but here's where we've been. We've talked about indefinite integrals and definite integrals. We've looked at an example where we can solve it using geometry and a different example where we can solve it using antiderivatives. So right now we're going to take a look at example 2 here. So when I see a picture like this, okay, let's zoom in. When I see a picture like this, I'm looking at these functions thinking, my goodness, these look so super complicated. I do not want to do the antiderivative. And luckily, these are all shapes that happen to be super nice. So for example, we have a triangle. So area of a triangle is 1/2 base times height. And I have a semicircle. And so that is 1/2 pi r squared. Okay, so let's use that to our advantage. So for question A, I'm looking to start at 0 and stop at 2, and that corresponds to this first triangle right there. So let's plug it into the formula. 1/2, the base is 2 units long, the height is 1 unit tall, and luckily I can reduce that, and so I end up just with an area of 1. Okay? Much easier than trying to think about how to take that antiderivative. Okay, next one. This one is saying start at 2, end at 6, and let's see what we get. Well, that is the semicircle. But it's below the x-axis, and we're going from 2 to 6, so it's negative. So we did a negative 1/2 pi r squared. And that equals negative 1/2 pi. The radius is 2 squared. And so I get negative pi over 2 times 4, or negative 2 pi. All right, let's move on. So question C, let me zoom in a little bit so you can see. Question C asks you to start at 12 and then go to 6. So what's different about this one is we're starting here and we're going this way. That means everything is the opposite of what you think. And so even though this triangle is above, we want to say that the area is going to be negative. So negative 1/2, the base of this triangle is 6, the height of this triangle is 3, and when we clean that up, we get negative 9. All right, now I know C was a little tricky, so I picked D to be a good review of that trick. So D looks very much like B. But what's different is the 6 is on the bottom and the 4 is on the top. So that means the area is the same, but the sign is going to be the opposite. So this area is not going to equal negative 2 pi, but it'll equal a positive 2 pi. Okay? So we're going to stop here for the end of part 1 of this video. Come back for part 2 and we'll pick up with more definite integrals. See you there.